So x minus mu, mu is, in this case, 10. And x will be whatever we want it to be, but in this case, let's just make it 11. Now, you have the cheat right below. You know 11 is going to line up with 1. And standard deviation is 1, so x minus mu becomes 11 minus 10 over 1. Moving over here, you see that's simply 1 over 1, which equals 1. So our z-score is equal to 1. Well, look, 1. And we see that's the case. Let's try it, slightly more complicated. Let's try it here for 210. Z equals 210 minus 200 divided by 10, which is 10 over 10, which is 1. And you can see that as we're 1, 2, 3 standard deviations away, our z-score is just 1, 2, or 3. It's very simple. And so this standard normal on the x-axis, these are our z-scores. Okay? Very simple. And so I will ask you how to take 12. Give me the z-score for 12 or for 11. 12 and 11, their z-scores are easy. What would happen if we did 11.5? I want you to think what the z-score would be. Think about it. What the z-score would be. This would be a mental check right here. The z-score. Okay? We know that that would fall right here. So what do you think that would be? Well, I think it would be 1.5. So let's check it out. 11.5 minus 10 over 1 simplifies to 1.5 over 1, which is just 1.5. Okay? And so we found our z-score of 1.5. Now, a z-score, or a standardized score, is just the number of standard deviations, abbreviated standard deviations, away from the mean. Okay? The number of standard deviations away from the mean. Now, we know from the empirical rule, 1, 2, 3, that's very easy. 1, 2, 3. But it's not always exactly easy, and so sometimes we'll want to find a z-score that's not a 1 standard deviation, 2 or 3. It's not clean and easy, so we need a z formula. So let's draw another picture. This time, standard normal. I want you to tell me on the standard normal how many standard deviations away would be 27 if we have a standard deviation of 5. Okay? A standard deviation of 5. Well, you can do this. You can do this quite simply. 27. What am I doing? Let's try this again. 27 minus the mean, yeah, divided by the standard deviation. 27 minus 20 over 5. This is 7 over 5. This reduces to 1 2/5, which reduces to 1.4. Very easy. Now, it works the same on the left-hand side or in the negative direction. Let's take a look. What if I ask you the z-score for 15? What would be the z-score for 15? Well, nothing changes except our x. Now our x is 15. 15 minus 20 is minus 5. Over 5 is minus 1. And you can see that that lines up exactly with minus 1. Standard deviation here is 5. So we are 1 standard deviation away. Once we have a z-score and we know how many standard deviations we are away, we can try to find the probability value for where we are relative to the rest of the population. For instance, IQ tests generally have a mean of 100 and a standard deviation of 10. Okay? So, filling this out, 110, 120, 130, and 140. Again, 90, 80, 70, and 60. And generally above 110 is considered genius category. And so, although IQ scores go on forever, go on until 180, and the normal curve goes on forever. Okay? What if I wanted to know how many people had less than 110 IQ score? Well, I know that this half, which I will color red, represents 50%. And I also know that within 1 standard deviation on either side is 68%, which means 34 here and 34 here. So I could easily tell you that 84% of people have less than a 110 IQ score. No problem. Pretty easy. There was no conflict. It was just very easy. The empirical rule, this is by the empirical rule. I'm not sure I spelled that correctly. Now, if I wanted to know what percent of people had below a 115 IQ score. This isn't so simple. 115 does not lie on an even z-score. 115, we would have to figure out, again, z, 115 is our x minus the mean of 100 divided by 10, gives you 115 over 10, which is 1.5. 1.5. My z is not so easy. There is a way that we can figure out from the table on E2, which is on page 792. On page 792, we